So good evening, everyone. Welcome to the SFPE Hong Kong Student Chapter events. This is Dr. Xinyan Huang from the Hong Kong Polytechnic University. So today we have a great pleasure to invite one of our colleagues, a very distinguished young researcher from Lund University, Dr. Nils Johansson. For those who are not familiar with fire research in Europe, I like to say Lund University is one of the largest fire research center in Europe, and they have a big fire lab there. And Dr. Johansson is doing his research related to the fire dynamics and also to the very applied fire engineering application, including the fire investigations. And the reason I'm particularly interested in today's talk is I read a paper written by Dr. Johansson last year that's related to the topic of using fire dynamics theory in the fire service activities. So I think that's a really good paper. I think it's the best paper I have read in 2020. So it's really a great pleasure to invite him to give more details about that excellent work. Okay, welcome.
So the agenda for today, first I'm going to talk a bit about the situation in Sweden and how we work with fire dynamics and connected to the fire and rescue service, because that's a bit of a context to this presentation. I'm going to talk about fire dynamics and fire rescue service activities as the title says, but there will be more of a focus on fire investigations actually. I will give some concrete examples as well. And if you have any questions, you can write in the chat or you can ask them after the presentation. Now first, the situation in Sweden. So maybe none of you have been to Sweden. I know, Huang, you've been to Sweden at a conference, but for the rest of you, it might be an odd country somewhere over in Europe. So it's located in Northern Europe, and it's quite a diverse country in terms of the type of buildings, the type of nature, and the type of response that the fire and rescue service needs to do. It's a long stretch country with only 10 million inhabitants. So I think that's maybe equal to what you have in Hong Kong. And they are sparsely distributed over this country if you look at a general picture, but in some places there are really no people at all. And in other places there's more people, of course. Half of the population is located to the largest cities, so there's some real urban areas as well. We have around 11,000 building fires per year in the country and around 100 fire fatalities per year. And the type of fires and the type of accidents that the fire and rescue service responds to varies, of course, around the country. Up in the north, we have mountain areas, snow and so on, and not many buildings at all actually, but forest fires a lot in the center, and then of course building fires in the big cities and regions, so on. So it's quite a diverse risk picture, you could say, in terms of what the fire and rescue service responds to in this country. When it comes to our fire engineering programs, we have 2 fire engineering programs in the country. One located in Lund, down in the south, close to Denmark, that you have here, and one up north, close to Finland, which you have here to the east. And in total, we around 80 students are graduated each year from these 2 programs. And it's a 3.5-year program that yields in a Bachelor of Science, but it's actually, it's quite a long bachelor. It's 210 ECTS, which is the points that we have at universities in Europe. The program comprehends of 1.5 years of basic courses, maths, physics, structural engineering, building materials, and so on. And then we have 2 years dedicated to fire and risk problems and courses related to them. So it's quite an extensive program in terms of the knowledge you get in fire dynamics and related topics. In order to become a high-ranked officer within the Swedish Fire and Rescue Service, you need to have two degrees, you could say, or two trainings. One is to have one of the degrees from these universities. So you have the fire safety engineering degree, and then you need 1 year additional fire officer training. This is a practical training, practical and theoretical, of course, at the Fire and Rescue Service College. This is not run by the university, it's run by the Swedish Civil and Contingency Agency. There's a high demand for fire engineers at the Fire and Rescue Services in Sweden. Each year, around 30 to 40% of these 70 to 80 students come and work at the Fire and Rescue Service. So we have 20 to 30 students starting in this area each year. So in summary, we have highly trained fire officers at our Swedish rescue services. They have 2 years where they have dedicated studies in theoretical fire dynamics and related topics. And then they have this 1 year more practical at the Fire and Rescue Service. So they should know a lot about fire dynamics. And this, of course, gives a great potential in using fire dynamics theories at the different fire service activities around the country at the different fire and rescue services. So the question is then, is that the case? Do they use this university education, theoretical knowledge, and so on when they go out and work in the practical field? Before I go on and try to answer that question, I just want to stop for a minute and say and ask, what is fire dynamics? And this is quite a broad topic, and maybe you can mean different things when you talk about this. But when I talk about it, I mean quite a lot. I talk about the fire chemistry, really, reactions and so on. We have a fuel, we have oxygen, water that will yield in water, carbon dioxide, and heat, of course. And this could be very different for different types of substances and combustion processes. It's about flames, the gasification, temperatures in flames, soot production, and so on. Burning of bigger objects, estimating heat release rates. That's something that I include in the area of fire dynamics. It's about plumes and calculating the plume mass flows and what will happen if we have a fire in a building. Production of different compounds. That's production of carbon monoxide, for instance. That's a part of our fire dynamic knowledge. Heat balances in enclosures to be able to calculate temperatures. That's also fire dynamics. Smoke spread in a building. Different types of modeling tools, more or less advanced, like computational fluid dynamics, CFD is maybe something you're familiar with. That's also a part of the knowledge you need in order to master fire dynamics. So as NIST puts it, National Institute of Standards and Technology in the US, they say that fire dynamics is the study of how chemistry, fire science, material science, and mechanical engineering disciplines of fluid mechanics and heat transfer interact to influence fire behavior. So in other words, fire dynamics is the study of how fires start, spread, and develop. So if we now go back and say, are fire dynamic theories used at the Swedish Fire and Rescue Services? In order to find this out, I did an interview study a couple of years ago, and that's presented in the paper that Huang referred to previously. I asked people that are out and working at the Fire and Rescue Services, also people who train these people at the Fire and Rescue Service College and so on, about the use of fire dynamics theory today and the areas that for potential use in the future. And I just made this simple presentation here, like in the preventative area, operational, that's actually out on the scene then when there is a fire, and investigative area. So after the fire has occurred, you might want to do some investigation or evaluation of the fire service response. So we see the current use, the potential and need, and the current theoretical understanding. And just going out and to talk to people about this and interviewing them, I saw that the current use, their picture of this at least, is that, okay, it's a fairly used within the preventative area. So you might use some fire dynamics theory in order to motivate a certain a requirement on a building or a business. They might need to use or install fire sprinklers because there is a fire dynamic problem that you or the person at the fire and rescue service has highlighted with the help of fire dynamic theory. That's possible. In the operational field, there was very little use of theory in that sense, according to the interviewees. The lack of time, things are happening fast. It's not possible to sit down and do calculations with the pen and paper or drag your laptop and do a CFD simulation, of course. It's not possible on the scene. Instead, different rules of thumb are used maybe, but they are not maybe always based on some fire dynamic theory. Instead, they're maybe based on experience from previous incidents and accidents and so on. So it's not that you can maybe reflect on the fire dynamic theory. Instead, you think in your memory, what have you been struggling with at previous incidents. And that could be a bit problematic if you are at a place or a scene which you have not seen before. And there may be a theoretical knowledge of, oh, it should be like this, could help you, even though you haven't had experience yet. The investigative area is also used sometimes from time to time, but not very much. Looking at the potential, the people saw a better potential in this overall. And in the current theoretical status, there's also some possibilities, but as we see, we have a higher level to go up to the potential. So there's still need for research and so in the area to be able to find and use different theories and methods in order to have the real potential of this. I also studied fire investigation reports. So in Sweden, it's mandatory to do smaller reports, but more extensive reports are not mandatory. They are done if the fire rescue service thinks it's a thing that they should investigate. So these are not occurring for every fire incident, but there is a collection of at least some fire investigation reports that are collected centrally at the central agency, and they're publicly available. So I studied 260 of these during some years to see if fire dynamics theory in some way was used in the fire investigations. I think that's maybe something you could assume, that fire dynamics theory is maybe connected to conclusions, hypotheses, and so on. But depending a bit on the scope of the investigation, I saw that in roughly 40% of these, some qualitative reasoning relating to fire dynamics was used. Maybe they talked about the fire spread and it was a flashover and so on in qualitative terms, so with words and no numbers. But then 60% did not use this, and instead they maybe referred to some experience or maybe not referred to the fire development or anything like that at all in the investigations. Looking in 2 of these 260 reports, there were some quantitative assessments. So you using calculations and numbers and so on, which I think is really a low number. I would expect that maybe you want to have some, of course, there might be some eyewitnesses giving you information about how things happened, but to control that and double check and maybe confirm it with the help of a calculation could be very suitable in many of these cases. So how can we use fire dynamics then in fire investigations? And I will give some first thoughts about that. Fire calculations can be performed in many ways. When we usually do a fire safety design, when it comes to designing the fire protection system in a building, we use a model or some type of calculation. Maybe we want to find the plume temperature, maybe we want to find the plume mass flow in order to design smoke vents or something up in a building. It could be something else. We want to look at the egress time and so on, and compare that to some time to critical conditions, which we calculate with a fire model. And the models can be very different, of course. Now I have the example here of plume temperature and plume mass flow, and then we use some type of plume model. So quite a simple thing, usually may be used as a sub-model in other type of calculations. In order to do that calculation, we need information about the heat release rate, the height where we want to find the plume mass flow, for instance, or plume temperature, and we might need some information about the fuel. So this is maybe traditional fire calculation that you would do. But now if we want to look at the fire investigation, we might want to find out what was the heat release rate. We come to the scene, we see that there has been a fire. What was the heat release rate? Maybe that's important for us to determine what type of fuel was used. Would there be a potential for fire spread to another building? That could be maybe used in some legal situation or something. So yeah, this is just an example. We want to find the heat release rate. We go to the scene and then we look, are there any patterns or traces or clues that we can use in order to find the heat release rate? Yeah, we see here we have a fire pattern, a typical V pattern here. And based on that type of information, we do a backwards calculation in order to find the heat release rate. This is called inverse fire modeling or backwards calculation. So that's a possible approach in fire investigations with the help of fire models derived based on fire dynamic principles. So some starting points could be that we have a hypothesis, more or less concrete. For example, we are looking at the starting object, maybe if that could be a starting object, and then we use calculations to confirm or reject the hypothesis. We might want to investigate alternative events, possibilities that could have happened if the fire rescue service would have acted in some other way. That could be something we want to look at in a fire investigation. Risk of fire spread, as I mentioned previously here, would there be a risk of fire spread if the fire service would not have come to the place, to the scene? What would happen then? Is another thing that might be of interest in a fire investigation. Analysis of the fire development and fire spread are of course also important. But something we need to take with us here, of course, is the level of uncertainty or a lack of certainty that we can have. In Sweden, we have a saying that something is between the thumb and the pointing finger. And that could indicate that, yeah, it's a rule of thumb. It could be, it's a rough estimate. But saying that, the distance between the thumb and the pointing finger could be quite large as well. So that's something we need to bring with us in this type of calculations. And there's several questions that can be asked in a fire investigation. How big was the fire? Was there a risk of fire spreading, and so on and so on? And of course, calculations from fire dynamic theories is just a piece of the puzzle when it comes to determining what happened during this fire incident. And when I looked at these fire investigation reports that I just mentioned, this piece was missing. Of course, the other pieces were there maybe, which helped to come to a conclusion. But additional piece in terms of calculation could even strengthen that conclusion, or maybe turn it in another way, if that's the case. Now moving on and looking at some concrete examples. And I will have a focus on fire investigations, but some of these can also maybe use during a preventative stage, trying to get a change into a fire protection system in a building when doing a review of that building or from the fire and rescue service, or maybe even in the operational stage if there is time enough to do any type of calculations or estimates. First, I will talk about flame heights. People who are familiar with fire dynamics and so on, I don't know everyone's background here, but we have possibilities to look at flame heights and do calculations on flame heights. And we have a definition of flame height, which is the height where we have the flame, or the height where we have flames above in 50% of the time. And also where the temperature is 500 degrees C. Flames are turbulent and random, and of course very difficult to estimate where they will be at a certain point in time. And that's why we talk about mean flame height instead. They fluctuate between 1 and 3 hertz, so 1 to 3 times per second, a normal flame. Just generalizing a bit, but when talking about the fire and rescue service and fire dynamics, we need to do things a bit more general. The mean flame height can be estimated based on simple rules of thumb. Maybe something that can be used on the scene, and so to estimate, okay, how big, now if the fire would spread to this object, how big would the flame be, and so on. These are quite rough estimates, of course, and there are possibilities to do more detailed calculations, maybe than in a fire investigation. We can use the flame height models to describe the fire development, confirm estimated heat release rate, or maybe estimate the risk of fire spread. And if we look at the fire investigation and we look at so-called clean burning, this is something that happens or is a fire pattern that we can see after a fire. Places where we have had intense heat, where the carbon has burned off. Carbon is combustible, and if we have temperatures of 700 degrees or more, this carbon will burn off. And we also have knowledge that a persistent flame will have a temperature of roughly 800 degrees C. So there is a correlation here between maybe flame height then and clean burning. And here we have a picture and an illustration of a fire scene, and we see that there's been some clean burning here. And based on this, we might go in and we can do measurements and so on to see how big this flame has been. There's also, of course, other fire patterns possible to look at the fire scene, like spalling and calcination of gypsum and so on. But if we now turn to our fundamental fire dynamic theories and look at some simple equations that could possibly be used in this case, not doing things too complicated, but using the simple equations, we have the Heskestad-Plume equation, which says that the flame height L depends on the heat release rate and the diameter of the fuel source. Quite simple equation, actually, derived from empirical fire tests. The good thing about this is also that it's fuel independent. So we do not need to figure out at the scene what was burning. We only need to know something about the HRR and the size of the fire, the diameter. Maybe we can look at the position on the floor and figure out roughly how big was the diameter. And if we estimate the heat release rate, which is usually done in a fire safety design, we can get a fairly good estimate of the flame height. If we have an error of 50% in our estimate of the heat release rate, we will only have an error of 20% in estimated flame height. So that's fairly good. we can be quite confident on our flame heights when we do a fire safety design. But what about if we now go onto the scene, we look at the clean burning and we measure how big is the flame? And we turn this equation around and do this inverse fire modeling, backwards calculations. And based on the flame height, which we measure at the scene, the size of the diameter, the size of the fire, we try to estimate the heat release rate. And of course, if we have a decent estimate of the flame height and maybe a small error of, let's say 25%, we will have a much larger error in the estimated heat release rate because of how this equation look. So it's could be quite problematic actually to do the backwards inverse calculation in this situation. But at the same time, we should know that our estimates at the scene can be actually done quite well if we have good fire patterns. When we've done labs in our fire investigation course, we let the students do this type of measurements. So we burnt on a gypsum wall, and they were then estimating the flame height. So 7 different groups of students looked at the same fire pattern and measured the flame height. These are just numbers. This is done in small scale, of course, so the numbers are small. But even though it's an exercise that tells us that they had a variation in the heat release rate between 14 and 21 kilowatts. And we see that there is a variation in the HRR, but it's actually not that very big in terms of fire conditions, I would say. But this is, of course, a controlled test and also good circumstances to do these measurements. But so I say this is a possibility that can be done in fire investigations and can be used, but you need to be aware of the uncertainties that can exist here. Another area is plumes and sealing jets. We know that the fire plume is what stretches up. It includes a lot of the air entrained from the sides, and that's the fire plume, consisting mostly of air. But it's hot and sooty, as we see in the picture behind here. And then we have the sealing jet that stretches underneath the ceiling. And here is several options to using plume models. I'm just throwing out a couple of plume models here on this page. There's a lot of different plume models. Maybe some of you are familiar with these, and they can also be used in fire investigations in different ways. It can be used to describe the fire development, confirm estimated heat release rates as well as the flame height could. Maybe look at activation of sprinklers and heat detectors. Maybe we know when a heat detector was activated, and maybe that can help us with the backwards calculation. There's of course fire patterns that could be of interest at the fire scene here as well. The V pattern or sealing circles are such examples, and here we see this V pattern, and based on this we could maybe determine what was the radius of this plume when it hit the ceiling, and here we also can determine maybe the radius of the plume and be able to do some calculations. Yes, here are some equations that I used in this example. B is the radius of the fire plume. Here we see this U pattern, and based on this, an estimate of the radius of the plume that occurred here in this fire event can be done. And if we do the normal calculation that you would do in a fire safety design, you see that if you have an error in the HRR that you estimate, you will have a small error in the plume radius. But now if we do the backward calculation, similar to as we did in the flame height, we see that there could be problems if we have an error in the plume radius of, let's say, 20% in our measurement, that would yield in an error in our HRR of maybe 70%. And that's of course problematic if we now, based on what we see on the scene, we want to do some more detailed calculations. Let's say we want to use the HRR that we find here in a zone model or a CFD model or something to see what would happen, or how was the fire spreading, or what was the concentration of carbon monoxide or carbon dioxide in this case. Was that the thing that the people died of, or were the potential for more injuries? That the questions, I'm just spitting them out really, is something that are of course of interest at the fire scene for the fire investigator, and how this then is used in the next stage. So it's really important here as well to have a good estimate of the plume radius if you're doing this type of inverse fire modeling. Melting of material is another thing. Based on what you see at the scene, you can see that, okay, maybe there are melting. In this case, it's a plastic lamp that's melted. If that's placed in the plume, calculations can be done. If it's placed in the hot upper layer, maybe calculations can be done on gas temperatures to correlate that with this melting behavior. And here is a similar graph, and based on this equation. And if we maybe can see what type of material was this lamp made of in this case, and based on that we can see, okay, this is the temperature that we will have the melting behavior. It looks like it's not entirely melted, just started to melt, so it would be in a certain range. And based on that, we can maybe do the backwards calculation in order to find the heat release rate, if that's what we are interested in. So based on things that we can see at the fire scene, if now the fire is not fully developed, because then these traces could be not seen, of course. We cannot see the melting if we have had a fully developed fire and very high temperatures. But depending on the situation, I just want to illustrate that there are tools that you can use to strengthen conclusions from fire investigations. Something that could possibly be done for a fully developed fire is to look at the maximum heat release rate. We know that for a fully developed fire, we will have a maximum mass flow through an opening. And if we have one opening or several openings, we can add this up. And based on this, we can do an estimate of the heat release rate, because we know that oxygen is required to have this combustion, and we can do a calculation for the heat release rate required for the ventilation controlled fire. And this will be the maximum heat release rate possible in this room. Quite a straightforward and simple calculation here as well. The only thing that we need to know is the area of the opening and the height of the opening. These are things that we can measure when we come to the scene, or maybe we can estimate if we are at the scene in an operational stage and see, okay, there's a fire over there, it's a door opening, that's the only opening, then we can estimate the heat release rate from that fire. There's also empirical data of how much water that's needed in order to put out the fire. This is, of course, rough numbers, because it depends a bit on how this water is added onto the fire, the droplet distribution, and so on. But still, it gives us some ballpark numbers, a rule of thumb, in order how much water do we need in order to put out a certain type of fire. Now, this is a picture in Swedish, but here we have the flow of water, and here we have the heat release rate. And we can see if we have a heat release rate of up to 5 megawatts, this is the type of building, and this is the type of fire, and this is the amount of water in liters per second that's needed. And increasing heat release rate, of course, we would need more water. Just using these two very simple relationships and equations, and we have a room that has a door that's 1 meter wide and 2 meters high. We can see that the maximum HRR, heat release rate, is 4.3 megawatts with help of this equation. And that means that we need a certain flow to extinguish that fire. And this is usually what one hose will give at the Swedish Fire and Rescue Service. So in order to put out this fire in this single room with this opening door, we need one hose. Finally, I just want to mention something about radiation, which is also an area that fire engineers usually master and is related to fire dynamics also, of course. This could possibly be applied at the fire scene or after a fire incident when you want to evaluate or investigate the incident and the circumstances. It could possibly be at the scene if we want to do a rough calculation of, will this fire spread to the adjacent building? Do we need to put water onto that adjacent building to prevent it from igniting, or put personnel at this position in order to prevent ignition and so on? It could also be something that's done after a fire incident to evaluate if a certain fire service response was motivated. Was it needed to pour water on that poor building over there? It now has extensive water damage. Was that the correct decision? Maybe someone could ask. You could do maybe calculations to then show that, okay, if we didn't do that, that building would be burning as well. Calculations of radiation can be quite complex. They can also be fairly simple. I'm not arguing for doing very complex calculations here. Instead, doing simple calculations, but having conservative estimates in order to be on the safe side, of course. If you look in the literature, you can also find values for critical radiation with the pilot flame. So that would be like the target value. If you reach these levels when doing this calculation here, you could maybe assume that there would be ignition. I'm not getting into the details on the different methods. Maybe you're familiar with them as already, or maybe it's something you want to look up in the future. But there's simplified methods as well, just based on the radiative part of the heat release rate and the distance to the target. This simple point source model can be used as well. And this is actually calculations that could possibly be done prior to a fire incident, to have this on some documents or something, just to go in and have a look. If you are at the fire incident, you can measure and see the distance. This is the distance in Swedish, this is the radiation, and you have a certain distance between two buildings. You estimate the size of the heat release rate based on the previous calculations that I showed with this simple relationship between the opening height and opening area. And you could maybe go in and see, okay, what is the distance needed between two buildings in order to be below, let's say, 15 kilowatts per square meter? And you see, okay, if we have a 10 megawatt fire, that distance would be 5 meters. And so on and so on. So this is the safe distance. If you have a really small fire, 500 kilowatts, the safe distance would be, of course, smaller. Just to have some ballpark numbers. This paper was mentioned in the start, and this is an open access paper. If you want to learn more, you can go in and read that. Maybe look in the reference list and so on. We do a course in Lund where I do lectures on this topic, fire investigations and the use of fire dynamic theories. So that's where I picked many of these examples from. Of course, in order to do this, it requires that you have some basic knowledge in fire dynamics theory and that area. And a quote that is usually mentioned when we talk about fire engineering, and I think really important in this area as well, is that we need to be aware of that when we do calculations in fire engineering, and especially in this area here that I talked about today, is that we are working with ballpark numbers and rough figures. And the models themselves are maybe not 100% correct. They are empirical, but they can be very useful if used correctly and if you know how to use them and what their flaws are. So that was my final words. Thank you.
Okay, thank you, Neil. Very, very interesting presentation. And
Yeah.
I'll just use my privilege to ask the first question. So, you mentioned many equations about heat release rate. So I'm curious why the heat release rate is important in the investigation process.
Yes. The heat release rate is maybe important in the next step. If you want to evaluate something more, you might want to know the heat release rate. If you would like to know what was the production of soot, for instance, and you'd want to do a simulation, a two-zone model simulation or a CFD simulation, you need to know the heat release rate. Was there a potential for damage to other buildings? You want to know the heat release rate, or potential of fire spread if the fire service would not be at the scene. That's something that's usually a thing in Sweden, is that when there is a fire, the fire and rescue service, they need to do an announcement or a written document to say, okay, was there a risk of fire spread? Was there a threat to other people if the fire service would not have been there or have been delayed and so on? So if someone has acted in a wrong manner or done something not good in terms of how they did things in the apartment or and so on, there could be maybe some legal thing against this person, and that the sentence and so on would be, of course, worse if there would be a larger possible threat to other people or other people's property. So it's and in that way, an estimate of the heat release rate can be something that can be used to argue that there was a threat.
Yeah, that's very useful. Actually, can be used to assess the future fire risk of a similar type of building or improve
Yeah.
the fire design.
Yeah. The heat release rate is the most fundamental parameter in fire safety engineering. That's often said.
Okay, so my student Sharon is collecting some other questions. So
okay, so hello Nils.
Hey.
We have one question from the audience.
Yeah.
So on fire scene, there is more practical to have an infrared camera to detect the exterior wall temperature of the adjacent building to justify if the fire will spread to it, rather than by the calculation. And the variation depends on the tier, not only fire size.
No. Yeah, that's true, of course. The calculations can be done much more detailed as here. And there's also technologies and tools that can be used, like infrared cameras and so on. If you want to do some preparation before you are at the fire scene or before that fire has also actually grown to that size that you need to do something, yeah, then you cannot measure the temperature because there's no fire yet. Maybe the fire will spread to the other side of the building, and then you want to be prepared. Do we need to protect the third building further away? Yeah, this is just simple ballpark numbers, as I said, and doing more detailed calculations with soot emissivity and so on. Of course, that can be done, and developing more detailed tools, maybe mobile phone apps and so on that can interpret data from infrared cameras and do the calculations. That's of course helps a lot if you have that type of tools available. Yeah.
Okay, thank you. We have another question from my colleague. He said the interview showed that the fire dynamics theory is poorly used in current fire operations. But from another point of view, can it be argued that it is the in-depth development of the fire dynamics that makes the operation so easy? So the firefighters don't have to think much about operating. Do you agree with his point?
Yeah, I think for like 95% of maybe all fire incidents and all fire responses that they do, there is no problem. You do your different tasks. You know the order of operation, what you should do. If there is a fire in an apartment, 2 people go in, they put out the fire and rescue. There is no difficulty because we know what to do. We have the experience and so on. And of course, then there's no need really to reflect on your fire dynamic theory and so on. But sometimes you cannot train for an event. You don't really know what will happen. So for the more seldom cases, I think it can be of a more importance to have the ability, maybe not at each and every fireman, but at in the background, maybe there are someone you can communicate with to give you expert judgment on a situation if it's something unknown or something very special.
Okay, we have another question. It's that the heat release rate and the radiation. There are other important parameters available in fire investigation and fire service activity.
So can you repeat the fire? I didn't hear the fire.
Is that the heat release rate and the radiation? Are there any other important parameters that are available in fire investigation and fire service activity?
Yeah, I think there could be several different other aspects. Now I focused on these two because I think they are maybe the most important and also mostly used. But as we see, the amount of water needed, that's of course associated with the heat release rate. But temperatures and so on can also be done, and I didn't focus now on gas temperatures in rooms, which is another area that could possibly be applied. In a way, the heat release rate, it often boils down to the heat release rate as being one important parameter. It's something you need to determine if you want to go on and do some further analysis. In most cases, at least. But it depends what the question is that the fire investigator at the scene has. What is the area of investigation? Do they want to find the fire cause? Do they want to learn about the fire incident? Do they want to evaluate the fire and rescue service response? Did they do the correct things, or could something be improved? Traditionally in fire investigations, in Sweden at least, there's been a focus on fire cause. and that's still important. Of course, the fire cause is something you want to find, and in many investigations that is the objective, but in other investigations that is one of the objectives. Another thing could be, as I said, to evaluate the fire service response, to learn from the fire incident, or the fire spread, or the building fire protection system, if that worked correctly.
I guess that heat flux is also quite important. You mentioned that there could be like safety distance between.
Yeah.
So is these kind of numbers written in the like building regulations?
No, no, not in the what's in the building regulations is a safe distance. So if you do the prescriptive building regulations, you follow the code more or less. There is a safe distance of 8 meters that should be maintained. And if you do performance-based design, there is actually no number for buildings. There's for people, but then you need to go into the literature and find your values and so on to work with. But then, in terms of building design, there will be more detailed calculations than the one I showed here now. So if there are 8 meters between the buildings, that's of course good, but we know that we have old building stock, and then we had other building codes, so the distances are not that, or they have maybe built supplementary buildings, and maybe you still want to protect them even though they are in the same facility, and so on. There could be a range of different aspects.
Some of these informal settlement of fires. Actually, these tin sheet houses are very close to each other. That's the reason fire can spread from one house to another. Definitely less than 5 meters.
Yeah.
Okay, so I think we have one last question from the audience. So is that you list several materials that show melting behavior in fire. It is known that the melting of plastic could promote the fire size. She is curious about how the melting of the glass and metal would affect the fire.
Melting of metal. Here the melting of metal is used as an indicator for temperature. So if we see that there is a melting of a certain material, we know that the temperature at that material has been at a certain level, and that's found in the literature. And based on that, we can then, okay, let's say it was 200 degrees here, or at least, then we can maybe use that information in a calculation as an input to a calculation in order to find some property that we are interested in, like the heat release rate, for instance.
Okay, I think that's no more questions. Okay, so let's thank our speaker, Dr. Nils Johansson again. And I also want to use the chance to remind all the audience, we have another webinar next week. So please register and join us. Okay, so thank you, Jonathan.
Yeah, thank you very much. Have a good day. Bye-bye.
Bye.